there. Mm. Okay, so we're back to the lecture in which we're discussing how to create a new process. Can you see my screen and hear me okay? Well, cool. Thank you, everyone. Yeah, we'll come back to this just for a sec. We'll come back to the slide on which we were stuck for a while last time, just to make sure that we all understand what's going on there. So what I was trying to say last time, and just to make sure that we all understand what's going on, and just trying to remind everyone what's going on in this thing, right? So again, I'll draw a diagram of what was happening, right? So again, so there was one process, and let me, for example, choose a green color here, which executes exec, right? So this process has an address space, something like this, right? This address space will have a user and a kernel part mapped, right? So because it's a well-created address space, right? And here, for example, you're running some kind of a main thing. So you have a text, data, and so on, stack, and a heap, right? So this process executes exec system call. It passes a string, something like bin ls in our example, and some arguments in order asking the kernel to create a new process, right? Sorry, asking the kernel to essentially replace its own address space with the binary of a new process, which has been the last of this example, right? So the kernel starts executing the exact system call. And what it starts doing, right? So right now we have a page table which maps this address space. Again, I'm drawing it green. The CR3 register, let it be green for a second, is also like it is pointing to this page table, right? So, but however, as we start working on this new address space, like as part of the exact system call, what we're gonna do is we're gonna start creating a new page table, right? So inside exec, we allocated a page for the page table directory, and we can call it page table, let's say new. And if we want to call this green one, it will be a page table old. And when I say page table, I refer to the entire data structure, entire tree of the page table, right? So okay, so we gradually say, look, we get add some pages to this page table, and the way it goes is the following. So let me again just move this chat around slightly. Probably my face is the least important on this slide. This cannot be minimized any further. Can we put it somewhere? Okay, put it here. And what we're doing is the following, right? So we said, okay, look, there will be a disk, right, accessible to us through a file system. And specifically, we'll be using read I, which reads an inode, read I method, right? So, and we don't know yet how the disk and how the file system, which sits here, stores this file, right? But we have an idea that if you pass an inode pointer, a pointer to the inode, then somehow it will like point to something on disk, and it will be kind of like a continuous file, right? And we will cover it later in our class, right? So we'll talk about the file system. So anyway, so we can read something from a file system, right? And so what we do here, we first read a header of the L file, right? So this new bin ls, so this is our file, this is ls sitting on disk. What it will have as usual, so if we draw it like this, it will have an elf header, right? The whole thing is elf, right? Similar to our homework. From the header, there will be a pointer to the program header table. I'll label it as a program header table, right? And this program header table, just remember the homework, will have pointers to loadable sections in the ELF, right? So maybe it's combined text and data, maybe just text, maybe it's text, and another one is kind of a pointer to nowhere, just says, okay, there will be like some kind of a BSS, which is not stored in the ELF, but you have to allocate space for it, right? So, and our goal inside the exact system call is to essentially like first read this ELF header right in memory. So we'll have an ELF header data structure in memory. Then read the program header table. We're not going to read the entire table at once, but instead we're going to run in a loop and read one entry by another, right? And after that, we say, look, the moment we read the program header entry, let's say entry one, like let's assume this one, right? We say we know that we're going to load the text section in memory. So we know it's address, like a virtual address, and we know the size, right? And at this point, we say, look, we were working on this page table, and right now, since it's a page table of a valid process, the very first step which exec did, it's allocated the kernel part of the page table. So essentially, it says, okay, I'm going to allocate the kernel part of the page table because this part, which sits here, and this part, which sits exactly here, will be the same, right? And so it's starting from like 2 GB and just map this 4 regions, which we discussed multiple times, right? So this part is already allocated. So maybe there are like some entries in this page table starting at around 512, which are already created by this alloc kernel virtual memory function, right? Okay, but when we got the size and virtual address of the text, right? We say, okay, got it. So, and virtual address might not be 0, by the way, but in x86 it's coincidentally 0, right? So we say we wanna load something here page by page. So essentially we'll be moving we will create a loop and we'll map essentially page by page. And that's fine. So you have a page table. Know that CR3 points to a completely different page table. It's a page table of the process which invoked exec. So this page table is not pointed by CR3, but we know how to map. So essentially, if we have a virtual address, we split it into 10, 10, and 12 bits, and those 10 will show us like the entry in the page table, and we will allocate the next level, use these 10 bits to essentially figure out the entry here, and of course, create a mapping for this page. And this page, obviously, we allocated it from the memory allocator, so it will have a physical page which backs it up. So my favorite color for this is actually gray, but we don't have gray. So let's imagine for a second there was a physical page, and I will draw it black in the physical address space, and we don't care about anything else. Like we don't care about where this page is located and stuff like that, right? So we essentially just have this page, and essentially we add this pointer to this page, to our new page table, right? That's what we were doing last time. And okay, cool. So far so good, right? So this page, this blue page, which I was just drawing here, is actually already mapped by this new page table, right? I'll ask you a question. Can you access this page? So this page with a virtual adder, we adder 1. Can you access it if you want to write something into it? Not directly. Okay, that's correct. So it means that you cannot use this virtual address 1 to access it, right? Why is that? Because if you start writing something, if you do something like, let's say, I'll draw you here, mem CPI, mem copy into virtual address 1, where will it go? It will specifically go to the location in memory, which is pointed by the current page table. So essentially, it will choose the virtual address here, go through this, because the hardware just blindly will try to do the move instruction. Inside memcpi, it's a loop of move instructions, right? We'll go through this page table, through the green page table, right? We'll resolve this virtual address, like same 10 bits, but instead of using them on this page table, it will use them on this, because the hardware is like, it thinks, okay, something is loaded by the CR3 register, right? But it will go into this page table mapped by the hardware. We'll figure out where this green page, which is at the same virtual address, is located, and we'll probably hit some other page, right? So that, not probably, but it will definitely hit whatever is here will point to the some physical page and physical memory. And the right, this memcpi, let's draw it orange, for example, some argument. Let's say some buffer that will, the data from this buffer go into this page, right? And I will give them names. So if you want to ask a question, so this is a physical address 1, and this is physical address 2, right? Right? Is this idea clear? And I will switch to chat and we'll try to answer the questions. So Gina is asking, what is the black part? Black part is a physical page. That's physical memory. So CR3 points to the old table, so it will look the old page table. Correct, Michael. So, okay, yeah. So is this clear? Is this just clear to Copper, Michael, and Jen, or is everyone on board on this? Okay, this is a good kind of like point to ask questions. What guarantees that virtual, okay, hold on. What guarantees, hey, you deleted it. I was about to answer. What guarantees that virtual pages in the new page table are correct, given that we are using virtual addresses from the old table? It's a multi-dimensional question. So what do you specifically, not sure what do you mean by correct? So in fact, we are not using. So we will not do this memcpi, because this memcpi, as I say, if we suddenly do this, it's not what we want. We really want this memcpi to hit this page. So the buffer, this yellow buffer, we want it to be here, right? Because it means that the data will be contained here, right? So this is actually wrong. We don't want to do it, right? I'm just saying that if we would do that, that's what would happen, right? But really, it's a wrong idea. So that we can't do that. We have to pick a different address. Let me just read here. Instead of this virtual address, this one, if we want to access this page, right, which is here in physical memory, we have to do a trick. And this trick, I was trying to explain it last time. I mean, I did explain, but I wanted to explain it again, right? So that's what we're trying to do. So maybe I'll come back to this, Smear, but let's move on for a second, and then you will ask the question again. So look, so we cannot put this virtual address. This is wrong, as we just agreed, right? So the question is, which virtual address we have to put here? So who knows the answer? Correct. P2V of which address? So Michael asks the question, so the walk page table function is basically a way to access the page address without using the hardware. Like if you temporarily can't rely on CR3, correct. So correct, yeah. So that's exactly what's happening because CR3 might be using some different address space. So it's, I mean, I agree, it's kind of a little bit multidimensional, right? So when you program, you never think about virtual memory. You just simply think about pointers. But in this world, in the world of operating systems, sometimes some pointers are temporarily invalid, right? Because they are valid in a different address space. And we have multiple address spaces, which is kind of funny, right? So we have an address space, the green address space and a blue one, right? And if you say, look, I want to use a blue pointer, I know that it will be valid in a blue address space, but it's not the address space which is used by the hardware right now because the green one is used. So you cannot use the blue pointer, right? So instead you say, look, I have to do a trick. I have to figure out allocation possibly in the green address space of the same physical page which this blue pointer is pointing to, right? I'll make you, like, just to make it clear, I'll make an illustration. So this virtual address, it's effectively a pointer, right? So like in your programming language, it essentially points here, right? But currently you cannot use it, right? Because if you use it, it will point exactly in the location in the green address space, but that's not what you want. Instead, what you say, have to, okay, is there a way to figure out an actual physical memory location, and maybe it's mapped somewhere in the green address space, and then translate the pointer from the blue to green and use it there, right? So again, maybe it's very unusual from the first time, but this is how it is. And this idea is not like super exotic. You can imagine that there are multiple address spaces, and we are constructing them because we're building processes, right? So each process will have its own address space, the green, the blue, something else, the pink color, right? And so some pointers might be temporarily invalid, right? And okay, cool. So now our trick is, like, if you want, I can draw you a different figure. I can, like, just looking for an empty slide real quick, maybe this one. So again, similar drawing, but maybe in a multidimensional fashion. So imagine you have a green address space, right? So, and the restriction which you have in your life in this, when you program in this environment, is that you always have to use the address space. You cannot use the physical memory directly, right? But essentially you say, look, I am currently working in a green address space, so CR3 points here. So this is the one which the hardware is using. A green pointer, if you have a pointer to a buffer here, is valid. It's okay, you can use it directly. If you have a blue pointer, like, which points in a blue address space, you cannot use it, right? Because the hardware will just verbatim take the value of this pointer and split it into 10, 10, and 12 bits, right? And what it means that it will, roughly speaking, it will be like pointing somewhere here, and you will suddenly override the memory of the green address space, right? But that's not your intention. But in practice, what you can do, you can realize that, okay, cool, there is real physical memory, right? And those two pages, like this green one is mapped somewhere over here, and I will probably draw it, I don't know, like let's make green color for the sake of it, but dashed lines, right? So, and the blue page is pointed, it is allocated somewhere here, and that's why we created a physical memory allocator. We track the location of each page. So if there is a page which is here, page 1, for example, we know that it's in the physical memory, it's here, page 1. If this is a green page, let's say page 2, it will be here in a physical memory, right? And now you say, look, my problem is that I want to use this blue pointer, right? I want to use it. I want to access this page, but hardware is using the green address space. The question which you do is you asking yourself is this page which is mapped, which is physically allocated for this blue page, page 1, is it mapped anywhere in a green address space? And by virtue of how we constructed the address space, the answer is yes. So there is a mapping actually, right? And this mapping, as someone was just saying, is actually, if you take a physical to virtual of the 1, you will get a virtual 1 address. and it will be somewhere over here. So it's the same page, but mapped in a green address space. And you say, if I want to use this pointer, I will do P to V of this pointer, and I will get this virtual address, right? And then if I do memcpy into this address, it will, since it's mapped here, it will land, the data land here in physical memory. And this is what I want. I'm really accessing this blue pointer, right? So does this make sense? So I was drawing multiple representations. So this is one is slightly more abstract than the previous one, but hopefully it explains what's going on. Okay, good. And you may end up in the case, like it might be in a different operating system like Linux. It might happen that this page is not mapped address space a priori. So you say, look, I want to access this blue page. I know the physical address of this page, but it's not mapped in a grid address space because no one mapped all, like x86 maps all accessible physical memory in every address space. So there will be mapping in this address space and this address space for all the physical pages, right? So by the way, of course, like since this page is mapped here, it will be mapped identical, like at the same location here as well, right? So that's in x86. But it may happen that this page is not mapped. And for example, you have to, in this case, you have to create a temporary mapping. So essentially you say, look, I know the physical address of a page. Imagine for a second that P2V is not working in this hypothetical new system like Linux, but you can map it. You can say, look, I will use the green page table and I will temporarily map this page into the address space of a green process, do my write into this page in order to make sure that I can reach this, like this location in blue address space, and then unmap it back, making sure that this is no longer mapped again in the green address space, right? So this is totally fine as well. So like real operating systems do that actually. Okay, does this idea make sense to everyone? Again, good point to ask questions. So we like spend some time on it, but that's totally fine. Not so clear about the Linux part. So the Linux part, I'm saying that it might happen that not every, like for example, you want to access this physical page in your current address space CR3, and it's not mapped. Like you say, look, this physical page, the mapping for this page, P3, doesn't exist in the green address space. So you temporarily map it. You figure out an empty virtual address, map it, do the write into this location, and so essentially map, write, and unmap, and destroy this mapping again. Just because you say, I don't want to deal with mapping all physical memory a priori, right? But x86 does it, right? x86 maps all physical memory from address 0 to address fistop to a virtual range, which is like a shift, which is 2 gigabytes plus 0 to 2 gigabytes plus fistop. Right? So they just, to avoid this case, then in which you might have a page, physical page, which is not mapped in a current address space, and simplify everything. They map everything a priori. Is this clear? How to get the unused virtual page? Good question. So, in a way, excellent question. So how do we get an unused virtual page? Does anyone know, can guess and tell me? So in practice, if you have, well, you do need to map it in a current address space. Okay, first let me answer the question of how do you get unused virtual page. In practice, you need to keep track of used and unused virtual addresses, right? Again, so let me just I just wanted to figure out yet another empty space. So for drawing, so what you do, like in x86, the address space is very, very simple, right? So again, you split it in 2 GBs. Your text section goes here. Your data section goes here. You have a stack sitting on top, which grows this way. This is the guard page. We will talk about it today. And the heap is growing this way. And a size of the current heap is known in the proc as Z variable, right? It keeps track of the size of the heap. So, which makes this one is used and everything on top is unused, right? And a kernel part is actually mapped. Everything is mapped from 2 gigabytes to 2 gigabytes plus stop, right? And plus the bias range here, right? So this is also masked. But in x86, this is unused. And you can, for example, rely on this fact and temporarily pick a page from here and map this page, right? Saying I will use this virtual address for whatever temporarily mapping I need, right? For a different address space. Well, if you just need one, good luck, just use this address. If you need multiple pages and you want to map them, then you have to create some kind of a data structure which keeps track of this, which parts of this region are used and unused. It can be the same virtual memory allocator, similar to this linked list. It can be a bitmap, right? And that's essentially this is what the operating systems are doing, like typical like Linux. But in Linux, the address space is less linear, so it's more complicated. So Linux says, okay, I will map some libraries here. I will have some gaps in the user part of the address space. I will have multiple stacks for multiple threads, right? So because there will be multiple threads running in a process, right? And the kernel part of the address space is also like not always like it has gaps and stuff like that. But the operating system keeps track of this layout and will eventually, I think, it uses a tree because it's efficient to like find a gap by descending the tree and figure out the unused virtual address instead of like linked list. Because if you say I wanna address of a like gap of a specific size, then I think it's faster with a tree. And so they implement this tracking, but it's not super hard, to be honest. Like it's just like a data structure which keeps track of unused virtual memory, right? But very good question. So yes, you need to keep track. In case of x86, it's not super complicated, right? Okay, next question. So is user virtual space 0 to GBs and mapped to physical space 2 to 4 GBs in x86? Not exactly. So look, I will go back. So we have this pictures all the time. Let me just show them to you. No, not this one. Like, and I don't have the slide deck. Let me quickly, because I'm on a single screen, so I wanted to just figure out, like this one is reasonable, right? So see, let's just pay attention. Pop, 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 pop. So if this is your physical memory, starting from 0 to, let's say, stop, in every address space, so imagine you have an address space, like for a process. It may be current, which is used by CR3, or it may be some other address space which you're creating for a different process. You always map this region from the address of 2 GBs to, with this shift, to 2 GBs plus stop. And all available physical memory, like all of it, like some of it is used by essentially by the kernel already, is always mapped in those addresses, right? So if you say, I want to access a physical page which sits here, in every address space, it will be mapped at this virtual address, which is physical to virtual of a physical address, right? So this physical address. Is that clear, Silas, and everyone else? Hopefully. Okay, next question. I get that there is a trick here to map to two different pages, and that P2V and B2P have to deal with kernel translation since those are constant. However, for user memory, this will probably not work as well. This will probably not work as well to just shift by kernel base. That's correct. Do we just rely on the page allocator and not worry about directly mapping specific virtual addresses to specific physical addresses? So not exactly sure about what you're asking, but let me try to answer. Let me go here again. I forgot exactly where is it. Where, like here, for example, right? So remember in our example, and I will use a different color, I will use this purple. In our example, our goal was to access this virtual address VA. Virtual address VA is a virtual address which is valid in a blue address space, right? So we just simply do, we cannot do anything like V to P of this VA, right? Because it simply will shift by 2 GBs, right? So, and will give us some physical address, but that's not a valid address because it will be just pointing somewhere. So it like will shift by 2 GBs, will give us a physical address somewhere over here, right? So somewhere here, and that's not what we want. We really wanted this page, right? In order to get this address, right, we walk the page table. So we take this address and we split it into 10 bits, 10 bits, and 12 bits. We walk the page table, in which this address makes sense, and this walking the page table will give us the faithful physical address PA1, right? Okay, since we know PA1, that's an achievement. We say, look, we know that any physical page is mapped by any address space, meaning that it will be mapped by the green one as well. And at this point, we can simply, we know the mapping, and we say, look, if we do if we do P to V of this PA1, it will just simply shift by 2, will give us the virtual address of this page in this green address space. It will be somewhere in a kernel region of memory, right? But this was mapped in every address space with plus 2 GBs shift, right? And suddenly it will give you some virtual address VA, this one, or I can say VA green. It's a virtual address which makes sense in a green address space, right? Because you can do this shift, right? Does this make sense now? Okay, so any other questions? Again, you have to kind of keep track of how I was drawing everything, but I think again, since we spent a fair amount of time on this, I think it should make sense, right, at this point. Okay, cool. So now we understand the deal with the two address spaces, right? And specifically, we can come back to the lecture and say, okay, this is exactly what load UVM is doing, right? So load UVM says, okay, just a reminder, we're gonna go back here for a sec just to start. So what we are doing, we're running conceptually inside the exec function, right? We're running in a loop which goes through all entries in the program header table, right? Reads each entry like into this location and local memory on a stack page. It first allocates the page for the virtual addresses which will be used by this section, right? So it's maybe text and whatever, text and data. And then it loads them by passing those virtual addresses into the load UVM function. So specifically alloc UVM function, if you have, let me make sure that we're back to those colors. So if we're back to those colors, and essentially say we're constructing a blue address space, right? So essentially we running on a green page table, but constructing a blue, alloc UVM will allocate the pages, right, for this virtual addresses. So there will be actually physical pages, and I'll go to black here to describe the physical pages, right? So let's say 3 physical pages, which will contain the text and plus maybe data section of a process, right? And so in a blue page table, this allocuvm function essentially makes sure that those pages are already mapped. They're still empty, right? So that nothing is there. And load UVM will specifically take the data from disk, which contains those text plus data for this specific binary, and will load them into those pages, right? And this is exactly what is happening here in load UVM. So essentially you say, look, I am starting from a specific virtual address in which I have to load the data from file. I will walk the page table. This is the blue page table. I take this address and I will walk it. So essentially I will split it into 10, 10, and 12. I walk the page table. I get the page table entry. It's a physical, because it's effectively a pointer to a physical address, right? In my color scheme, I should circle it black. Then I will take actual address, like I will just mask the flag bits with this pt adder macro. We'll get the physical address, right? I know that this physical address is mapped in a green address space, right? And effectively what I'm gonna do here, I will do this, I will take this and turn it into my green address by using P2V, right? Now we all understand because I just had this drawing, right? So it's a green virtual address, and I will pass it into this read function, read node function, right? And that will essentially load from disk into this green address, right? Now it's kind of completely simple, right? So the color scheme helps us from blue to green, right? And black is an intermediate step. Okay, so load UVM, any questions about it, just by the way? Everyone is good? Good. So, okay, so UVM, so just another slide, which I sets up the stage for the discussion. Then we have this drawing, and finally read an inode into the memory. And at this point, we have the binary of the file in the blue address space, right? So we're totally cool on that. So we say, look, like we understand that the blue is there and the process is almost ready to run. What we need to do is to make sure that it has a stack, right? Because for the process, yeah, you can set up the instruction pointer to the entry point of the process. Let's say it's the main function, right? But in order to run it, you need a stack. Plus, you need stack in order to pass the arguments to the program, right? Because main follows the calling convention and it receives the argc, the number of arguments, and argv array of pointers, right? So I'll explain this now. So how do we allocate a stack, right? So like load UVM did this from disk. So we loaded this from disk, right? So this is the process text, process data, and this is exactly how it looks in x86. What we're gonna do is we allocate 2 pages. One page for the stack itself, so the ESP will be pointing here. And in order to prevent the case where you running out of stack memory, like essentially because the one page is only 4096 bytes, so that's the size of your stack, right? And if you allocate something large on a stack, maybe it's an array, and you say, well, my array will be 4000 bytes, plus you have some local variables, there is a feasible chance that the stack, which will be growing this way, can run into the process data section and will simply override the data in global variables in the data section, right? So it's totally fine because the stack just grows, right? And this is writable memory, right? So in order to catch this case, essentially just try to crash early. Most operating systems today introduce a concept of a guard page. So the guard page is actually not accessible. So it's neither read-only nor writable. So essentially the user bit is not set. So the user bit is set to 0, which means that the kernel can access this page, but the user cannot. And the moment ESP points into this page and you try to do a move instruction or a push instruction or a call instruction, which touches this memory, you will get an exception, right? So, and then the operating system says, okay, well, you ran out of stack, and it will probably kill the process, terminate the process, or pass the control to the debugger, or sends you as like a kill signal or something like that, right? In x86, the process will be terminated, right? So let's see this idea, the concept of a guard page. Is it clear? Good. So let's take a look at how this is allocated. Naturally, very simple. Right now, SZ has the size of the address space. Let me erase everything on this slide. So SZ points here, right? Because SZ started from here, and as we were loading these sections, we were incrementing SZ. So we say, look, let's round it up to the next page and set it to this. And we will allocate, again, we will use this function, which allocates data in a blue, in a blue, not green. Erase everything, switch the color, in a blue address space, right? It allocates 2 pages. It says, okay, I need 1 page for the stack, 1 page for the guard. These 2 pages will be allocated consecutively because you say I'm starting from SZ and going to SZ plus 2 pages, right? And SZ is already rounded up to the page, right? The page boundary. 1 page is enough for stack. For x86, yes. For modern programs like, anything essentially. For C, in many cases, it's enough, right? It's your choice. Languages like Java, Rust, they allocate a lot of stuff on the stack. So I would say that the typical stack in a real operating system like Linux is something like 64 kilobytes, but it's actually configurable as well. So operating system will allow you to configure the stack size. So if you're going to be running out of stack size, you can reconfigure it, right? But for x86, it's enough. Just make sure. That's why, roughly speaking, that's one reason why any programming class will teach you not to allocate a lot of space on a stack, because really it's limited. The heap is much larger. The heap in x86 goes up to 2 gigabytes, right? So roughly speaking, you can have up to 2 gigabytes minus some small range which you allocate for text and data section, but the heap is giant, but the stack is very small. Recursion is very bad in x86. Yeah, I used to ask this question on the exam. I have a function foo, which is recursive. You pass an argument, a, how many times you can invoke foo. A good answer would count everything, like all the data which is allocated on a stack, like arguments passed to main, and then every time you invoke foo, A takes a spot because it's a calling convention, return address, then the old EBP pointer, right? And then you keep counting how many times you can invoke foo, right? Not many, right? Because you can, even now, even if you like using 3 by 4, it's 12 bytes to do in one invocation minus this, I don't know how many bytes. So that's not that many times, right? Even if you divide 4096 roughly by 10, you'll only get roughly like 400 times, right? Something like that. But again, more careful arithmetic is there. But again, I'm happy that you can reason about it, right? So I will ask you, hopefully we'll be able to answer. Someone will ask you how many times you can do it in Linux. You can ask a question, so with what stack Linux is running, they can say, well, maybe you can assume any stack size. And I say, well, I've seen that Linux runs with like 64 kilobyte stack. Now you will start counting. You can also say on this job interview whether EBP is maintained, and you can say, like, remember, realistically in modern world, even the C compiler will not maintain the stack frame, right? So, but the calling convention is there on 32-bit systems. Don't forget that on 64-bit systems, it's a little different. So A will be passed in registers. So all these details are important, but you're well set to kind of answer all of it and then impress your interviewers with your knowledge of how the stack works, right? Okay. Sorry, slight detour. Back to this. So let me erase everything on this slide again. You allocated 2 pages, but since you want the guard page to be protected, you clear the U flag, the user flag on this page. Essentially, there's a function in x86, which again takes a page table. In our case, this is a blue page table, right? And it will remove the user accessible flag for this page. And if the user code accesses this page, it will trigger an exception, but the kernel can access, right? Because even remember the checks, all the checks which x86 is doing on the system call arguments are relevant to SZ, meaning that If there is a gap, you can say, why is that I'm wasting this guard page? Because literally this will never be used for storing any. Let me switch off the alarm for a sec. Otherwise, we will wake up, which is not good, right? I don't want to stop. Good morning, everyone. So wait, back to this. So we simply cleared the user accessible flag, but the page is wasted. The physical page here is wasted. And a better technique would be say, well, let's not map this page at all. The only reason x86 maps this page because the user might trick the kernel to make like pass an argument. Like, for example, remember an argument that is called like a pointer to a buffer pointing into the guard page. And remember, the checks are done, pointer will be relevant to size, the size of the address space. And after this check passes, the kernel can use this pointer. But if the page is unmapped, it will trigger a page fault. And x86 cannot handle a page fault. So there is no machinery for that. It's just simply a simplification to make it simpler kernel. And so essentially, this is the reason why the page is allocated, but the user flag is removed. The user accessible flag is removed. Got it? Any questions? In real operating systems like Linux, of course, the guard page will not be mapped. And the checks for the system calls will be just more complicated. So they will validate the fact that actually Linux, of course, can handle a page fault, and then like it can optimistically access this address. And then if there is a page fault, it will do the checking and say, look, you're pointing into the guard page, then most likely you're corrupt, and it will terminate the process. But x86 is much simpler. Okay, so we got it, the guard page moving forward. So we, at this point, remember this, all the steps which we've done for loading, for implementing exec. So we created the address space, the blue, loaded it from disk, allocated a stack. Now we're gonna push the program arguments on a stack, right? Because the program starts this bin_ls, which we're creating, bin_ls. Inside, of course, there will be a main function. And main function, does anyone remember what arguments main takes? Who can tell me? Correct, argc and argv, right? So the first argument is an integer argc, I'm sorry, argument count. C probably stands for count. And the second is, I forget exactly how they say, maybe char pointer to pointer argv. So it's an array of pointers. So let me explain it a little bit better for you. So this is it, right? So main will have argc and argv. So when you invoke the following string from bash, the convention on POSIX is that the program itself will be pushed, the string, the name of the program, will be pushed as an argument, right? So argc keeps track of how many arguments will be pushed all together, and that will be 3. Argument v will be a pointer to a string program. Argument 1 will be a pointer to a string hello, and argument 2 will be a pointer to the string world. And that's why everything is a string, since you're passing from bash. That's why this is a char pointer. If you want a more accurate depiction of that, this is another argument where you call a myprog from shell, right? And you pass 3 arguments, dog, cat, and frog. argc will be 4 because on the argv array, pointer 0, which is a pointer to a string, myprog, which ends with 0, by the way, but it's a string. Argument 1 is dog, pointer to a dog. Argument 2 is pointer to a cat. And argument 3 is pointer to a frog, right? So by the way, all of these, since these are arguments, right, argc and argv, there will be on a stack, right? So if I draw you a stack, and this is how x86 does it. So imagine this is the stack, right? Remember that the very first argument, if you have main argc and then argv, argc will be at the very bottom of the stack. So this will be argc, and it will contain 4, right? This is the stack grows this one way. This is argc, and then this will be argv0. So argv0 will be a pointer to my program, right? I'll ask you a question: where will you put the my program or my prog? Where will you put the string? Anyone? Like, can you put it in a data section? Cooper says on a stack, and he's correct. A const section, a good guess, but no. Why? Because you cannot put the string in a const section, because this is my prog, and you're invoking it from shell. You can make up anything. It can be a dog, it can be whatever, ff, right? It can be whatever, fish. You cannot enumerate all the words in the universe in your const section. These strings which you're passing to this program are not known a priori, right? User generates them, types them by hand, for example, right? So there is no way to put it in a data section or a const section, right? So you're going to put them on a stack, but this is exactly the reason. So essentially, what you're going to do when you create a new process, you're going to put my prog as a string, individual bytes as a string, right? Plus 0 here on a stack, and you're going to put a pointer to this location on a stack. And this will be argv0, similar for argv1. You're going to put the, argv1 as a dog. So you're going to put a dog here on a stack somewhere with a 0. That will be your bytes. And you'll put a pointer like this on a stack. And similar for whatever the other two, right? But you got the point. So everything goes on a stack. Can you hit the guard page by just passing too many arguments? You can. Good question, Zane. You will be a penetration tester. So in fact, totally, because yes, try it in x86. And in fact, run the boot into x86 and run this experiment. But that's a great question. I mean, that great observation. I don't exactly remember whether the x86 will guard against this case when it creates a process. So go ahead and read how the process is created. But yes, if you pass a string which is longer than a page, then you are in a guard page. I didn't talk about it, but what if you pass the 8,000 bytes on a stack? Since you spill over the guard page, you can actually override the data section as well, and even everything here, because those are writable pages. So the guard is a best effort to prevent the stack overflow. But if you really allocated a chunk which is larger than a page, then you jumping over the guard. And it's a real problem in real operating systems, like, because no matter how big the guard is, you can always allocate a bigger chunk on the stack, and the stack pointer will jump over the guard, right? In a safe language like Rust, to prevent the stack overflow, when you do this, the runtime will check the stack size. When the runtime allocates something on a stack, it will check the size and then essentially make sure that the guard is not jumpable over. But this is the real attack. So people figure this out, attackers, and they jump over the guard page. But this is a great observation. So that's not a bulletproof solution. So you have to design something different if you really want to protect against it. Good point. So any other questions? Okay, good. Let's take a look real quick how, I mean, the code is a little bit too low level. So, and at a high level, it's a loop. I mean, if you understand the high level picture that you have to put everything on a stack, it's not hard to write this code. Reading this code is a little tricky. So essentially what it does, it goes in a loop. It says, okay, I will push all the arguments on a stack. So essentially it has a helping function copy out, which again, internally converts between the green and the blue address space because you're currently running on green, but you have to convert all the addresses into the blue. So it essentially uses the stack pointer as an address, then like copies the strings which you're trying to pass on the stack, remembers the locations of those strings in a temporary data structure, which is called useStack. Then on a useStack, essentially, it says, okay, I will know that like it's kind of like it will create a prototype of the user stack, but in fact, it's just like it's kernel data structure at the moment. So it will create a fake return address because it wants to layout of the stack to match the calling convention. It will push the argc, like at the very bottom there will be a fake return address, then next to it will be argc, and then you will like push the argv pointers there, and you'll use the copy out. But again, I don't want to spend a lot of time. So again, conceptually, it's very, very simple. Just everything goes in a stack. If you care about it, you have to read this source code, but let's not spend too much time on this, right? Because we will get stuck. But the moment we're done, at this point, the program is ready to run, right? We have to switch the page tables, essentially say, okay, look, we were in the exec system call. We're currently on a green address space of the old process. We're going to switch to the blue address space of the new process. And this is what you're doing here. And at this point, after you did the switch, you're ready to deallocate the old address space. You're not going to fail at this point, right? Okay, so this is exactly what exec is doing. If the first line of exec is 6310 at around 6398, so first of all, exec is not a giant function, less than 100 lines. You say switch user virtual memory. So essentially, like at this point, you will like switch to a new page table, and then you see deallocate the old address space. And let's take a look at these functions, right? Since we use this, first of all, like again, I wanted to ask a question like, what is this address space which we're deallocating? And the answer is the address space of the old process, right? So in our diagram, this green address space is the address space of an old process, right? So this is the one which called exec, right? And this is the new address space of the BNLS. Now we said, okay, CR3 is actually will be pointing to this new address space after we switch the user address space, and this address space will be deallocated, right, with this function which frees the address space, right? And if I ask you a question, how do you deallocate an address space? It's kind of an easy question, but I still wanted to ask. Just wanted to check how much time we have. So what's the algorithm? How do we allocate the address space? Return the pages to the memory allocator. That's good. So which pages? In a way, you're clearing the page table, the pages for the old process, free physical pages, correct. But I mean, at a high level, yes, you're right. What I wanted to say is that the page table itself contains the page table directory, a bunch of page tables, page table 1, there's some kind of page table, I don't know, n, and those are pointing to real physical pages, right? And not all entries are actually allocated. So some of them might be free, right? So your goal is obviously walk this tree, understand which pages are allocated, first free this page, return it to the memory allocator, allocate all the leaves, right, mapped by this page table, free the page table, walk the tree, deallocate everything, and then deallocate the page table directory itself, right? So that's the algorithm. I just wanted to make sure that this is clear to everyone, right? So let's take a look at how x86 does it, right? So again, at a high level, the algorithm walk the page table, deallocate all the physical pages mapped by the page table, like I said, deallocate the pages that contain the page tables, right? So level 2 of the page table, and deallocate the page table directory, right? And this is the code. So essentially the function free virtual memory in x86, it does the following. So it says, okay, we're gonna descend into this deallocate user virtual memory. So what it does, it walks the page table, right? So it says, I'm gonna go, and the way we invoked it is from the address 0 to current base, right? It walks the page table. If the PT is present, right? If it's not present, it just simply skips it. If it is present, it takes the physical address of this page, and essentially, since the kernel virtual memory allocator stores the virtual address, it does the P2V and returns it back to the allocator, right? And sets the PTE to 0, right? And that's in a loop, right? For the entire address space. So the user part of the address space, right? Agree? Not super hard. After that, essentially say, look, I deallocated it. And at this point, we say, look, we're going to deallocate the page table entries, right? So here we say, by the way, if the entry in the page table directory is present, we will take the virtual address, return it back to the kernel memory allocator, right? At the very end, you deallocate the page table directory itself. Agree with this? So again, conceptually very simple. Just wanted to make sure why P2V here. P2V is always there because the kernel virtual memory allocator, remember it has a head, it operates in terms of virtual addresses. So every page, like here, it stores a VA, right? Because it will write into this address. It will typecast the address of a page to a node type and will set the next field, right? So all of these pages, all of these addresses are virtual pages, right? But you convert between them. So this virtual address is V2P will give you V2P of VA will give you a physical address of this page. That's the translation. But that's how, because again, like if you want to access the page, you need a virtual address. Good. Okay. And just to recap, what we achieved here over the course of 2 lectures is that we understood how exec works, right? And we now can create a new address space. So I'm not going to cover fork. So fork will be covered as the homework assignment. So essentially, I will ask questions about fork on the quiz this week, right? So last week I didn't assign a quiz, but this week there will be a quiz about the fork, right? So, but we understood exec. Any questions about exec right now? All good? Okay, so this is nice. Is there a way to reuse the old address space mappings from the old process since they deallocate them eventually anyway? Well, you probably can come up with some exotic optimizations where you create and destroy processes very, very often. Like, for example, you can imagine a web server like Apache, which forks a process every time it processes a new request. The question is, Apache doesn't really exec, it forks, right? But maybe there is a use case in which you're going to exec. And if you really want to optimize for this case, you can come up with optimizations for how to reuse the address space, right? But again, like maybe let's take it offline and welcome. I'm happy to talk about it during the office hours and how we can reuse it, right? Anything else? What I wanted to talk about now, we still have 10 minutes. So we talk about the exec, right? So one process can create like we didn't talk about fork, but let's imagine we have a fork. So process can create new processes, and this process can exec and replace its address space. But the real magic still is not kind of covered. So how does the operating system x86 creates the very first process? This is what I want to discuss now. So let's take a look. Again, very end of the main function. We did all the initialization, right? So we did like kernel memory allocator, the kernel page table, bunch of other things. At the very end, there is a function which is called user init, and it creates the very first user process. Let's take a look at how it works. Again, at a high level, it's reasonably simple. We say, look, we will allocate a data structure in a kernel for the new process, right? Essentially, the fork will do the same, right? Exec already allocated it, so that's why we haven't seen it before. But when you create a new process, you really need a process data structure. And this data structure contains information about the process, right? So essentially, when you're inside the user init, you call this function allocproc, which returns you a pointer to the new process data structure. And this new process data structure, remember I told you, if someone asks you on the job interview, what is a process? Just quickly look at this slide and you will answer this question because it contains all the information. Of course, it's a minimal process. It's process in x86, but in Linux, it's very, very similar with more fields, more corner cases, but kind of the same, right? It has those fields which we've seen before. So it has a field which covers the size of the address space. We've seen how exec uses this to essentially load the binary of the process from disk to memory, right? It has a pointer to the page table. It has a pointer to the kernel stack. Remember, each process has a kernel stack because when it is preempted with an interrupt, the interrupt executes on this kernel stack because the user might don't have a valid ESP value, right, to crash the kernel. It has a state for the scheduler, whether the process can run or it has to wait for something like for the IO, for example. It has a process ID, so you can identify processes in a system. It has a parent process, and the parent process might be waiting for this process. Remember, when we were working on a shell, we were forking and waiting. So essentially, when the process terminates, the parent will be notified, and if the parent is waiting, it will exit the wait system call. It has a trap frame. We will talk about it, but we know what the trap frame is. So this is what gets saved by the interrupt handler. And then we will see how the trap frame is used in a context switch later. But right now, we've seen only the trap frame. We were seeing how the trap number was used to dispatch between different system calls and exceptions, right? It will have a context, and that's to implement the context switch between the processes. We'll talk about it next week. It has a channel. So essentially the process can wait when you essentially enter the kernel and say, I want to wait for data arriving on a pipe. So we'll see how this is implemented, but the channel is one field which essentially allows the process to say, I'm going to wait on this channel. It has a logical flag, whether it's still alive or the kernel has to like essentially deallocate all the data structures. It has a file descriptor table, right? Like we talked about it a bunch, but this is just an array of pointers to the struct file. We're going to cover them when we talk about the file system. It has the inode, again, part of a file system, which points to the current directory. That's when you type something like /, this current directory, this dot comes from this field, and it has a name. So mostly for the debugging purposes, so you can show the user that like ls is running, right? When I kill my Wacom driver, essentially I do ps list all the processes in the system and then pick a process ID and then terminate it with a kill command, right? Okay, so that's the process data structure. Not surprising, right? So all the fields, if you can explain all these fields like I did briefly, and know what these fields are. And again, x86 is a very good playground. So you can read if you say, look, I don't really understand what this field means, right? And we can talk about it later, but really you can search for the source code and understand how this field is used and then answer this question as well. Like that's how you answer those questions if you ever asked about it. Okay, so but at a high level, we got the process data structure, right? Every process has to map the kernel space, and we do the same. So we use this map function, which maps the kernel part of the address space, starting from 2nd gigabyte up to 2nd gigabyte plus fstop, right? It's not super new, right? We did it. Set up kernel virtual memory, returns a page table, which was the page directory field of the process, right? You may run out of memory, then you panic and say, oh, we cannot create a new process. At this point, x86 terminates. It doesn't recover from that. And here is the main trick which x86 is doing. It says, okay, I have the kernel part of the address space. The question is, what are we going to put in a user part of the address space? What kind of code we need to execute to create, like, to keep the system going? Can anyone tell me this? Logically, you want something to run there. Let's take a look. x86 uses this trick. It looks like something that runs in code's main. Correct. But I will give you like a slightly, like, they do it in a slightly more elegant way. So they include the code of the very first process as part of the kernel. So essentially, remember in the homework, we provided the symbol end to make sure that we can map up to the end or past the end, right? So in a similar manner, x86 uses the binary code of the init process and creates these two symbols, start and size of this process. It uses the linker in a very similar manner. And this will be a tiny assembly sequence. This tiny assembly sequence will execute the exec system call, right? Because since you already have exec, you can rely on the functionality of exec to create a real good process. But this it's called the trampoline code of the binary init process will be essentially loaded in memory first. And it uses the same function. It uses the function init UVM. It says like taking the page table directory, map this assembly binary of this specific size, right, into one page of memory. That's very easy. So essentially, what it does internally, it just uses one page init UVM. It allocates the page, and essentially, since it's the init code is passed as an argument init here, it will use it here to do this mem move function, essentially from init to the size. So this, whatever the assembly code is pointed by the init pointer, will be like, it allocates a page, sets it to 0, maps it in a page table with address 0 here and size page table. It's writable and user accessible because you have to run it. And then you simply copy this assembly code into address 0. Let's take a look at what this assembly code is, right? So I'm just like having this slide. This assembly code is very, very simple. As I was saying, it will execute the exact system call. So it will do int 64, and it will load the EAX register with the exact system call number. And it has the strings to say, look, by the way, I want to create exactly this command. So I want to execute exec, and I will execute the init process. I will exec into the init process. Init process, exec, we already know how exec works. So we know how this address space of this first process will be replaced with the memory of the init, right? And so it has the string, which says, I really want in the data section, and it has a string in it, and it has this argv array, which it creates here on the stack, and it just passes them to the system call, just everything by hand. But you can imagine that it can be done, right? So essentially just like return address fake 0 and two arguments, argc and argv on the stack, right? Okay, cool. And after that, it executes the exec system call, and it turns this tiny assembly init.code.s file into the init process. And the init process is essentially will run and create a shell for you, right? So what I wanted to say, what I wanted to say here is the following. This is the init process. So the init process itself, this is, if we exec into init looks like this. It says, okay, I will fork, and I will replace myself with the shell. And this is what you see when x86 is running. So essentially, this is the shell. If the shell dies, this child exits, but the loop essentially comes back here. In a parent, you wait for it, and it will again fork and will restart another shell. So that's why you cannot kind of like exit from x86. If you kill the shell or exit from the shell, it will just start a new one right away, right? And that's how init works. So, okay, let me stop here because we are exactly at a half past the hour boundary, and I will very quickly finish those couple of slides which I skipped here, which essentially make sure that the kernel actually starts this init process, right? And we will either do it next week exactly, or maybe we will wait until we cover the context switch and then come back to this later. But anyway, thank you, everyone. And I will assign a quiz. We'll try to do it early, maybe today, maybe tomorrow. It will cover the topics for the last 2 weeks. And so work on it, be ready. I will send an announcement. But thank you, and we are done. See you next week in person.